We've now discussed each of the types of transformations of functions and how they're reflected both in the equations and on the graphs. In particular, we saw how a vertical shift could be represented by f of x plus d. We saw how a horizontal shift could be represented by f of x plus c. We could reflect about the x-axis by multiplying a negative out front of our function. We could reflect about the y-axis by multiplying a negative to the input of our function. We could stretch and compress our graphs vertically by multiplying by some factor outside of our function, and compress and stretch horizontally by multiplying the input of our function. And so now that we've explored each of these transformations and how they work individually, what we might ask is, well, how can we combine them? How can we put all of these things together, perhaps in an expression like a times f of b times the quantity x minus c plus d, and utilize a combination of these transformations to start from some parent function and end with the graph of a fully transformed function given all of these parameters. Now, to do that, we want to make sure that we have the order of the transformations correct, right? So in some sense, very much like when we operate on things algebraically, there is an order of operations. We're going to have a similar order here with the different transformations of functions. So you might be familiar with the traditional order of operations from an algebra class. This is usually recognized with the acronym of PEMDAS, which sometimes you can remember by something like "Please excuse my dear Aunt Sally," but it stands for parentheses, exponents, multiplication, division, addition, and subtraction. And this dictates to us the order at which we need to do any of those operations if they're all combined into a single algebraic expression. Now, for something like a times f of b times x minus c plus d, this in itself is an algebraic expression, and so can sort of follow those same rules, which will lead us to the order of transformations. And so in particular, if we were to evaluate this expression as if it was just any old algebraic expression, using our order of operations, we would have to first start with what's inside the parentheses here, the x minus c. Now the x minus c, as you might remember, is our horizontal shift. And so in terms of the order of our transformations, the horizontal shift is where we'll start. Once we've done what's in the parentheses here, the next step in evaluating this algebraically would be to look at multiplying times b. In other words, a horizontal stretch or compression. From there, since we're all still multiplying, we want to make sure that we take care of the multiplying by a. Now, whether this is positive or negative will determine whether or not we have a reflection, but usually it's easiest to do the stretch vertically first and then worry about the reflection later. Not because it necessarily has to be done this way, just because it tends to be easier to keep track of. And so next we'll have the vertical stretch or compression, followed by the reflection if there is one. And lastly, after we've done everything in parentheses, we've done all of our multiplication, then we'll take a look at the addition and subtraction, in this case just the plus d, which is our vertical shift. And so our order of transformations will be horizontal shift, compressions and stretches, reflection, and then vertical shift. And so keeping that in mind, let's see if we can put all of those together to graph the function f of x equal to 2 times the quantity x plus 3 squared minus 1. And we'll do this by starting with the parent function, x squared, and transforming it one step at a time from there. So if we begin first with x squared, this would be our parent function here in the black dashed line. we want to work through our order of transformations in order to, one step at a time, get towards our end goal of graphing the function f of x equal to 2 times the quantity x plus 3 squared minus 1. Now we know our order of transformations here, and that means we're going to start with our horizontal shift. And so in this case in particular, we have x plus 3 as our horizontal shift, right? So instead of f of x minus c, here we have f of x minus negative 3, right? That's where we're getting the plus 3 from. It's the same as minus negative 3. And so in this case, we have c equal to negative 3, which is less than 0. And so that's going to signify that we need to shift 3 units to the left. And so we can take all of our points on our graph here, negative 2, 4, 2, 4, and 0, 0, all of those 3 key points, and shift each of them over to the left by 3. And so we'll start with negative 2, 4, shift that over by 1, 2, 3, which will end here. We can go at 0, 0 and shift that over by 1, 2, 3 to end here. And 2, 4, shifting that over by 1, 2, 3 will put us here. And then we can sketch our function by connecting the dots. And so this blue graph here has taken care of our first transformation, the horizontal shift. Now taking that graph and copying and pasting it into a new one, we can now work with the next step in our order of transformations, which would be, if necessary, to do a horizontal stretch. In this case, we don't have one, right? We don't have any number multiplying by x, so we don't have one here. Leading us to our third step, which would be the vertical stretch. And so next we'll look at a vertical stretch, which in this case is represented by 2 times f of x, right? We have 2 times our quantity squared. So that means we're going to be stretching this vertically by a factor of 2. So in other words, if we take our original coordinates, like negative 5, 4, we can multiply the y coordinate, or the f of x value, by 2. In this case, giving us negative 5, 8. Similarly, if we have negative 3, 0, 0 times 2 is just 0. And so that will give us negative 3 times 0. And also with negative 1, 4, multiplying 4 by 2 gives us 8 as well. And so we have negative 1, 8 for our third point. Plotting each of these, we have negative 3, 0, we have negative 5, 8, and we have negative 1, 8. And so if we connect the dots, our function should look roughly like this. Taking that blue graph now and copying and pasting it into a third space here, it's usually helpful as you're doing this, if you're writing it out by hand at least, to kind of move one at a time like this. But if we take that graph here and copy and paste it here, we can then take a look at our next piece, which would be to shift this vertically by 1. Right, we don't have any reflections here. This is positive after all, so we can skip that step and move just to our vertical shift, which will be our last in this case. And so shifting this one here, we can see that our value for d is going to be negative 1, right? In this case, we have our function, our previous function, minus 1. And so d is equal to negative 1, which is less than 0. So that's going to tell us that we're going to shift down. And so taking each of these points here and shifting them down by 1, we'll move negative 5, 8 to negative 5, 7. We'll move negative 1, 8 to negative 1, 7. And we'll move negative 3, 0 to negative 3, negative 1. And we can once again kind of roughly sketch that graph here and then copy and paste that into one more graph here, which now represents our final answer. And so this last one here would represent f of x equal to 2 times x plus 3 squared minus 1. Right? This has a horizontal shift left by 3, a vertical shift down by 1, and a vertical stretch by a factor of 2. Now, these are types of problems that may require a lot of practice as they come in a lot of different variations. One thing that might help is to utilize Desmos here. If you graph the general function and then create different parameters for each, you can play around with these sliders to see just how they will affect the graph as we manipulate them both in the positive direction and the negative direction for the two shifts, C and D, and for greater than 1 or less than 1 for the two types of stretches, A and B. And so I hope you found this video helpful. I will include this specific Desmos link in the description of this video in case you want to utilize it. But otherwise, I hope this has given you a sense of how we can take all of those individual transformations and piece them together and combine them using this order of operations to begin with a parent function like x squared and ultimately morph it through a series of steps to get to graphing an expression like 2 times the quantity x plus 3 squared minus 1. If you do have any questions, as always, please reach out. I'm happy to help. Otherwise, I hope you have a great rest of your day.